Okay, so I just hit the record button so that I don't forget. But yeah, thanks everyone for dialing in, and I see we still have a few more people dialing in, so that's great. But yeah, welcome everybody. And before I introduce Peter, I just wanted to draw everyone's attention to one new feature. I don't know how useful this might be, but please do let me know if it's useful or not useful. But I recently installed a live transcript app on Zoom. So it's called Rev, and it provides closed captions. So I was testing something out for a meeting I'm helping to organize, but you might see a new CC live transcript button at the bottom of your screen. So if you click that and select show subtitle or view full transcript, it should show you closed captions. So I just installed it for something else to see how it works, but it's tied to my Zoom account. So we'll have it for Friends of Lunar Volatiles meetings as well. And yeah, let me know if that's useful. And if you turn it on and want to turn it off, you can always do hide subtitle as well. So in my experience, it does pretty well. It doesn't always get the science words, but yeah, just so you know, in case anyone noticed that and was wondering. So our speaker today is Petr Pokorny from NASA Goddard, and he is going to be talking to us about his work on meteorite bombardment of airless bodies. So, Petr, I will hand it over to you, and feel free to introduce yourself in more detail. But I will give you as much time as we can. So, before we get started, I guess the only thing is, if anyone has questions, would you prefer if we interrupt you, or would you prefer if we wait until the end?
Oh, you can interrupt me anytime you want.
Just okay.
Jump in, and I find it better.
Sounds good.
Yeah.
Okay. All right. So with that, then I will remind everyone else to mute unless you're speaking, and I will hand it over to you, Petr. Take it away.
Okay. Thank you. So hello, everybody. I'm Petr Pokorny, or Petr Pokorny, whatever you like. I've been doing meteoroids for quite a while. It's been almost 10 years. So hopefully I will show you something you don't know, or at least tell you something cool about meteoroids. So today we'll be talking about these airless bodies in the inner solar system. So I picked the three largest ones we have, Moon, Ceres, and Mercury. And we'll talk about how meteorites impact them and what they do. These three particle bodies are great because they were visited by spacecraft, so we have a lot of data for them, and I think it's really cool that we can actually access these bodies and see them up close. So before I start, I would like to thank my collaborators without whom I would be struggling to finish this research. So thank you all for helping me with this, and being great collaborators. It's a great group of people. And so today we'll talk about the motivation, why we actually do meteorites in the solar system, why we study them, and about three papers that I published with my collaborators in the last 3 years. On the right side, you have QR codes that lead to those papers. So if you want to scan them, feel free to do that. It worked on my phone, so hopefully it'll work on yours. Yeah, so why do we actually study meteorites, and what do they do in the inner solar system? So we know that meteorites impact Earth from various observations like meteors and spacecraft, and we know it's around 40,000 kilograms a day that Earth accumulates from meteorite impacts. And we also know that the average velocity is around 15 to 20 kilometers per second, so it's high velocity impacts on Earth's atmosphere. The kinetic energy is something around 10 to minus 7 joules per square meter per second. So if we accumulate this for 100 years, we get something like 1 handgun bullet shot per square meter, which is quite a lot, I think. And on long-term scales, it can mean something interesting for surfaces of bodies. of course, this is not delivered in one shot, so it's very different from the shot from a handgun, but still quite interesting. And we have planets like Venus, Earth, and Mars that are protected by atmospheres, so they have meteors. Unless you have a really big meteoroid, they do not interact with the surface. On Earth's bodies, you have no atmosphere, so there's no protection. So on Mercury, Moon, or Ceres, meteorites can directly impact the surface, and they can transfer the energy to the surface, and something interesting can happen. In contrast to solar radiation that is concentrated to one point source, which is sun, almost point source, meteorites have broad ranges of direction. So they might possibly, as we will see, impact even the permanently shadowed regions. So they might not be permanently shadowed from meteorite impacts. So first we will start meteorites at the moon. So why did we focus on the moon and meteorites in general? So our main goal was to create a calibrated model for the moon and use the established dynamical models, combine them together, use some observational constraints, and see if that model that we developed from 2010 to 2014 actually can work for the moon. Because we had several spacecraft visiting the moon, and some of them had capability to measure some meteorite-related phenomena. And the model output from this work would be a model that provides you meteorite mass, velocity, direction, and number flux for any place on the moon and for any day of the year. So effectively, the complete information about the meteorite environment that you might need. So the first thing that we set to do was to fit the data from LADEE, LDEX detector. So it's Lunar Dust Experiment from Soleil 2016, for example, or Hurrah 2015. And on the right-hand side, you have the observations, which are the gray columns or boxes with the green points. And the model itself, combination of 4 different populations, main belt asteroids, Jupiter family comets, L-type comets, and Oort cloud comets, is in the blue. So it's on the right-hand side here. And our first goal was to fit this. So we combined all models, and then we did a lot of fitting, some Bayesian minimization. And we found out that we can fit very nicely the night side measurements. So from, let's say, 21 hours local time up to 6, 7 a.m. local time. But we lacked a lot of ejecta on the day side. So this effect was present every month. So we concluded either the meteorite environment is weird because we cannot fit both sides, or there's something happening on the day side. So in the original paper, we concluded that there's some day side effect missing, something connected to the temperature of the surface or the loading the surface with some sun radiation related phenomena. There's a sort of a secondary explanation that was published by Soleil et al. 2021 that's connected this daytime increase in meteorite flux or the dust cloud flux to beta meteorites. One problem is that LDEX has no data between 12 and 20 hours of the local time. So we don't know if this effect is real or not. We don't know if the model is correct even for those local times or not. But from what we have now, we can say that the model works pretty well. As a bonus from this, we got the ratio between helitypes and Oort cloud comets we didn't have before. So it was really great to have it and to do this. So I would like to point out that we were able to model the shape of that LDEX saw. LDEX saw the dust cloud density that is around the moon. But we were not able to get the magnitude of the dust cloud, how many particles there are. About that a little bit later. So when you take meteorites impacting the moon, from the model, we can get the impact velocity distribution. So the distribution of velocities, impact velocity, is much different from what we see at Earth, because the gravitational focusing is different. The moon is much smaller, so the gravitational focusing effect is much smaller as well, because the mass is smaller. the escape velocity of the moon is 2.4 kilometers per second, while Earth is 11.2 kilometers per second. So since the meteorites at 1 AU have relative velocities with Earth and the moon less than 11.2 kilometers per second, there's a huge spike for Earth, which is this blue line on this plot, while the moon shows you the entire range of impact velocities. For the moon, the impact velocities peak at 9 kilometers per second, but they extend down up to 40 kilometers per second, and then around 50 to 60 kilometers per second, there's a retrograde population coming from long period comets. So this mass flux shows you that, okay, the most of the mass is in the slower meteoroids, but the high velocity portion could be highly energetic, and it can overcome actually the low velocity portion of the population in terms of energy or impact vaporization that they deliver to the surface. So what do we have for impact directions? So the meteorites themselves, as we show in this plot, are not constrained to ecliptic or any particular direction. They have very broad direction, impact directions. Here we show the ecliptic latitude, which might relate to just thinking that the lunar equator is sort of aligned with the ecliptic latitude, which is not entirely true, but it's 1 degree off by 1 degree. And then we show here that the impact velocity versus ecliptic latitude stretches up to totally polar orbits. So you can have impacts from that impact poles head on. So effect on velocities that are up to 30 kilometers per second. So that tells you that no matter where you are on the surface of the moon, you can get hit by meteoroids. And the mass flux, of course, comes from close to ecliptic directions, but as we showed before, we can go to highly inclined orbits, and we can impact the surface from anywhere we want. Of course, this shows you that the lunar equator experiences most of the flux, and the energy as well is concentrated close to the equator. So for the time variations, you can see two things. We can see that the lunar orbit itself is causing 1 month sort of variations, and then there's another component to it, and that's yearly variations. That's the sun and moon orbit around the sun. And when we look at it sorry, in a global sense, we can see that it oscillates around 14 to 1500 kilograms per day for the entire year. And the variations themselves, the monthly variations are really low. That's a couple percent at most. And the year variations around 5%. We are able to fit these two variations to sign fit. So in the paper, we give a nice analytical formula, and you can get a nice equation just to express this mass flux quite easily. And in this figure, we show also that the highest mass flux is at the perihelion passage, which is was here around January 14. The lowest is in the aphelion. That has to do something with the profile of the zodiacal cloud. The zodiacal cloud is more dense, close to the sun. So this was quite interesting for us, because we were not expecting we can just fit it into sine function, but it was really a nice fit. So before I start saying something more about the effects of meteorites on the surfaces of these Earth bodies, I want to introduce a few quantities. So we have the mass flux, which is just mass of meteorites that scales with the mass of meteorite itself and the number of flux, and then you have cosine of the angle that the meteorite impacts the surface patch. Then you have energy flux, which is just the energy of meteorites. Impact vaporization flux. For impact vaporization, we use this simple formula that we got from Sintala 1992. You might have a different formula, your favorite formula. I'm not saying that this is a perfect representation, but it's something we used. And for higher velocities is almost equivalent to energy flux with some factor. For lower velocities, it can be slightly different. Then we have ejecta production rate, which is scales with velocity as 2.46, power 2.46, and it scales with the impact angle with cosine to power 3, which is very important because the impact angle itself is very important for this impact ejecta production rate. And then another thing that we can, for example, measure is the area of craters that are produced by meteoroid bombardment. So just take an area of the meteoroid that's impacting the surface, and then we multiply it by just an impact to crater area ratio, which we found was 63 in paper Koshny and Green 2001. And that gives us the area of craters that the meteoroids produce on the surface. Okay, so when we focus on impact vaporization, the formula is here on the bottom, we see that for different lunations, there are slight variations, but on the average, you can assume that it's sort of constant throughout the 1 month. And these four maps show local time versus the selenographic latitude. So at 0, you have 0 selenographic latitude, you have the equator. And you can see that any time of the year and a month, the local time is the peak of impact vaporization is always at around 6 a.m. in the morning, which is the dawn terminator. This is due to the fact that the most energetic part of the meteoroid environment comes from this direction. So these particles are impacting this direction head on. And then you can see that when you go to the polar regions of the moon, that then you get non-zero vaporization still. So we get a lot of vaporization on the poles. The only thing that we see that decreases the impact vaporization is around dust terminator, around 18 hours local time. When close to the equator, you get almost 0, because those are the impacts that are hitting the moon from the back when you assume that you are moving forward on the Earth's orbit. So this is what we call anti-apex impacts. So these maps, they change a little bit throughout the year, but this is the image we see for almost every day. The meteoroid environment itself is quite stable for this impact vaporization. And from the meteoroid model, we can get the impact vaporization in some SI units. So you can directly apply it to your favorite area on the moon and see if the impact vaporization flux is enough to cause some effect that you study or not. Okay. So another thing that we can study is the ejecta production. So you can see that the plots look similar to impact vaporization, but the shape is different. The shape is different because the cosine of the impact angle is now cubed. It's not just linear. And that constrains the impact ejecta production close to the equator. On the color scale, we show 2 color scales. We show the model ejecta mass production rate, and then we show the predicted LDEX lunar density. And if you remembered the numbers from the very first figure I showed, you would see that in the figure they had the density was 0.3 particles per cubic meter. And now we expect something like 100, 200, 300. So the model predicts 3 to 4 orders of magnitude denser cloud than what LDEX measured. And that's a problem. That's even a problem in astronomy. I was told that 3 to 4 orders of magnitude is a little bit too much. So what is the problem? So from this little formula here, you can see that you cannot change the mass of meteoroids because that's some range that we observe. the mass flux itself is constrained by what we see on Earth. So maybe we can change it by a factor of few, but we cannot change it by 3 to 4 orders of magnitude, because then we would see no meteors, and this would be difficult. The impact velocity itself, that's difficult to change because that's the orbital dynamics. The impact angle is difficult to change because, again, that's given by the distribution of orbits. The power can be changed. It doesn't have to be 2.46. It can be something from 2 to 3, but it doesn't give us enough change to change it by 3 to 4 orders of magnitude. So the only thing that we can change is some constant c that was determined in laboratory measurements, and that gives us the yield of regolith, how much it actually produces. And we think that that's the problem. We don't have the yield of regolith, of the lunar regolith, constrained properly. There's another explanation for this, what can cause the problem, and it could be that the LDEX observation itself might be giving us the number or the dust density that it's giving us. It's not that it's not correct, or it might be correct, but we don't know if it detects the entire truth, if it detects 100% of particles, or if it detects just a subset of it. But again, it would be very difficult to explain why LDEX is observing only 1,000 or 1/10,000 of the entire dust cloud. So this was one of the conclusions, that maybe the laboratory measurements are not enough. They are not constraining the ejecta production at the moon, or for the regolith that we have on the moon, and we should redo them with something more recent. So to summarize this paper, the model can reproduce the LDEX measurements in terms of shape, not in terms of magnitude. The meteorite mass flux is around 1,400 kilograms a day. It's mostly cometary. 95% is coming from comets, 5% is asteroids. The impact velocity range is very broad, peaks at 9 kilometers, goes down to 2.4, but it can go up to 60 kilometers per second. And it can impact the surface from all directions, and even on very steep angles. And we experience a lot of variations, but they are not that important because the monthly variations are negligible. And the impact vaporization rate itself also has negligible monthly variations, around 6 to 8%. No, those yearly variations, monthly variations are 4 to 5%. So for every quantity we studied, the monthly and year variations were not as important. There are some importance, it's around 10%, but it's not very important. So it can be, as a zero order approximation, considered constant. And we see that the impact vaporization and the ejecta production rate is very localized in the local time. And it gives a broad range of latitude. So if you assume, or you don't have to assume, the moon is rotating. So when you average it over one rotation, you get nice stripes that are, the effects are decreasing with the latitude effectively, sonographic latitude. So this was the first paper that we did, the meteors at the moon. And from that, we were thinking, what should we do next? Because we have this nice model, and there's a lot of...
Can I interrupt
to
ask
sure,
a question before you go on to the next one?
Sorry.
Maybe I'm misunderstanding, but how come in one of your early figures where you were plotting energy versus latitude, how come you don't see that one, like discrete bumps for meteor streams, like the Leonids and so on?
Yeah. Sorry. So this is the meteoroid model for the background, the eclectosporic background. I forgot to say it. The meteor streams are not included in this because from Earth measurements and from what we see at Earth, we see that the meteoroid background is around 90 to 95% of our meteors that are detected at Earth. So those 5% coming from meteorite showers or streams are not included in this model to make it easier to interpret, let's say. You can add the streams on top of this, yes, but they are not included in the work. Yeah, sorry about that.
And then a second question: when you disagree with LDEX by 4 orders of magnitude,
yes,
maybe I just haven't a clue, but how was LDEX sort of confirmed? That is, how do you know they're not really off by 4 orders of magnitude?
Oh, we don't know. Well, we talked about it when we were writing the paper, and we concluded that it's highly unlikely that LDEX is off by 4 orders of magnitude, but you're right, it might be true.
No, but presumably in their published results, they give an argument that their answer is reasonable.
Yes, but I'm just saying, like, there's always a possibility. Like, I don't take anything as certain, but yeah, I'm just saying that might be another alternative explanation, but most likely explanation is that the yield is much smaller than we assumed.
Okay, thank you.
Yeah.
Peter, do you mind if I just comment on that too real quick?
Oh, no, you are the expert on LDEX.
Just to comment on LDEX, it was a pretty simple instrument, and the even order of magnitude, we got hit like once a minute, and we got 1 detection a minute. And from that, with very simple arguments, you get to what the density should be. And so it would be pretty tough for us to hide a factor of 1,000 more impacts in what we got.
Okay. That's the reasonableness argument. That's fine.
Yeah.
Thank you.
I missed something too, if I could quick get a clarification. Where your prior plot that David was asking about, yeah, is this accounting for meteoroids from all directions?
Yes, that's all directions. It's effectively average around for the longitude is averaged, and this is just like a cut, like 2 degree. You know,
So do you have anywhere that it's, maybe I just missed it. Do you have anywhere where it's plotted just the ones that are coming in like from way out of the ecliptic? Or is that in your future presentation that we just haven't heard yet?
like these are all or meteorites from any direction. So
Right, but I imagine it's dominated by ones that are coming in and from something like near 0.
yeah, that's the red blotch here. Effectively, this is the dominating source, but it's very extensive. So the meteorite environment itself is very broad. Even the close ecliptic sources extend to 20-30 degrees in inclination. So they are not just in the ecliptic. The zodiacal plot is very dense, close to the ecliptic, but the orbital distribution is quite broad.
Yeah, well, I'm trying to ask is if you showed one that gave like the intensity as a function of the angle it's approaching the moon from, or maybe you're about to show one in your next section.
Well, I think this is the ecliptic. The ecliptic latitude could be the same as, because if you the equator of the moon and the ecliptic itself, it's like off by 1 degree.
Oh, okay, I got it. I was misinterpreting this plot.
Okay,
I'm good. Thank you.
okay, cool. Yeah, so this is effectively the direct impact latitude on the moon.
Oh, okay. So like the ones down at 80 degrees are,
-80.
they're coming at the moon from an 80-degree angle from the ecliptic?
Yes, so 80 degrees is you are hitting the North Pole almost.
And it's coming straight down at the North Pole?
Yes.
Okay, yeah, thank you.
So that effectively shows that like there are no permanently shadowed regions for meteoroids because you can just hit them head on. Okay. Thank you for questions. It's great. So with this model, as I showed before, we were thinking what to do next, and we found this beautiful data sets of topography available for the lunar poles. And so you're thinking, how can we connect this model of meteoroids with all these directions and masses and velocity distributions with the topography itself? So for that, we had to develop a ray tracing code. We didn't have to, because we couldn't find anything that would fit our needs. So we developed a ray tracing code, combined it with a meteoroid model, and then the objective was just to compile high-resolution maps of meteor bombardment effects, which we published, and they are available for anybody to download. So if you look at the mass flux at North and South poles, the South Pole is on the left side, North Pole is on the right side. You can see that the mass flux itself is quite uniform on anywhere on those poles and any location. There's some variation, but the median flux is, let's say, it's 0.39 grams per square centimeter per second times 10 to minus 16. And even in the most shadowed region, you don't get less than 5 to 10% below that median flux. The dark spots just show you that it's just a color scale, effectively. That's not zero, that's just color scale. So it was kind of surprising for us because we were expecting something more drastic. Then if you focus only on permanently shadowed regions, which we define here as their slopes is below 10 degrees and the maximum temperature that appears there is less than 110 Kelvin, then those surface areas that are shown here, you cannot get, as I said before, below 10% of the median value, or maybe 12% somewhere on the North Pole. There's 1 or 2 surface patches that got really low. So it was quite surprising to us because it shows you that meteorites can access any place on both poles without caring much about the local topography. So what was interesting was when we calculated the ejecta production rates. So we used the same formula as we used for LADI, even though it didn't agree in the orders of magnitude. We had 3 to 4 orders of magnitude disagreement, but we figured, okay, somebody can rescale it, or we can rescale it later if necessary. So when you apply this to both poles, you get a slightly different picture than what we saw from the mass flux. So what we see is that the higher the slope you have, imagine you are on the pole, so you are 90 degrees off the ecliptic almost. So the higher slope you get, the more impact ejecta you produce. So some craters with very steep sides, very steep rims, produced a lot more ejecta than their floors, for example, like we see here for Shackleton here on the South Pole. So it was very interesting. We didn't expect this because we expected that the ecliptic, the high energy portion of meteorite environment will be totally blocked, but it seemingly enhances the ejecta production rate. So what we decided to do, we just took all surface patches that we had on both poles and checked how does the slope and the ejecta production rate compare. And we found this very nice relation that we could fit a 2-degree polynomial to it, and we got nice increase with the slope. Effectively, the higher the slope you get, the higher impact ejecta production you get. So that was interesting to us, and it was very surprising. Maybe everybody expected that, but yeah, it was surprising to us. So it shows you that the higher slopes are effectively more efficiently processed, which might mean that you deliver more energy to those higher slope areas and you create something called mass wasting, for example. So the summary of this paper, I know it was short, it was on a few figures, but we saw that the local topography has very small effect on meteorite-related phenomena. While if you take solar radiations, you have huge changes. It's very significant, the local topography. So since the meteorites can access effectively all permanent regions without any problems, we see that the meteorites should process the lunar poles at very similar rates. So we can provide highly energetic events to permanently shadowed regions, which can affect the volatile contents of the permanently shadowed regions that are protected from effectively the solar radiations. So we don't expect that meteors would cause any difference in aging, because as you saw before, we have this 10 to 20% differences in the impact production rates, for example, or the delivered energy is also 10 to 20% different for all around the pole. So the only thing that we see that the crater rims and sides with higher slopes are more efficiently excavated, that can loosen some material, that can produce mass wasting and bury some force. But other than that, we couldn't find any more effects. So if there are any different excavation rates of ice, there might be material related. If we have different mixing ratios of regolith and water ice, it can cause, it can change the yield of that mixture, and you can maybe excavate it much more efficiently for more ice content material versus something that's more mixed with lunar regolith. So that was our conclusion of this paper. If you have any questions, let me know. Okay, I hear no questions. So
I do have one.
Oh yes, sorry.
So you said that the amount of ejecta or processing is cosine cubed of the angle of incidence.
Mm-hmm.
Is that, so are you taking like the local slope and adjusting the angle of incidence then?
Yes, so the ray tracing code allows us, we know the slope for every single surface triangle. So we can calculate the angle between the triangle itself and the meteorite direction. So.
Okay, so like if you have a steep slope, that's almost like you're irradiating near the equator instead of at the pole. So you end up getting a lot more energy transfer that way.
Yeah, if you think about if you build a chimney on the pole, then you are
exactly
getting the super high energetic impacts. Yes. So the more you are facing to the ecliptic, the more energetic impact you get.
Okay, this might have, I think this is wrong telecom for this, but this might have a bit of an effect on tall structures that are being proposed for the poles.
It could be.
All right, thank you.
Hey, Peter, I have a question too. So how much does the direction of the slope matter? You know, is there sort of an east facing, west facing kind of trend?
We looked into that, and since when it's rotating, we didn't find any longitudinal preference effectively. If you have something symmetric, if you have a symmetric crater, like for Shackleton, for example, it's very symmetric. So we didn't find any east-west, any difference between eastward and westward facing craters, for example.
Okay, yeah, and that's just, it gets averaged out over the course of the day.
Yes.
Okay.
Wasn't that an effect of the model? I'm trying to remember. You showed a slide of the 4 different quarters of the moon, and that there was some difference, but didn't you say you then neglected that difference?
No, we don't neglect it, but it's really small, and if like the rotation of the moon is not the fastest, you are right, but if you accumulate, if you check it over several years, it evens out effectively the effects, because sometimes the meteorite environment is coming the strongest is on the east location of the structure. A few years later, it's on the west. So, you know, it evens out over longer time scales.
Okay.
And even if there is something, it should not be more than a couple % difference. Okay. Yeah. We tried to, we did one crater, and we looked for the entire year how it changes, and it was really negligible. So we didn't, maybe we commented on that on the paper, but yeah, it's a good question.
Sorry, can you put maybe some perspective, long-term perspective on this? If I think about the yellow ring I see on Shackleton,
yeah,
can you make some estimate of like how much soil displacement that represents over the age of Shackleton?
Yeah,
Big number or a small number? I just don't know.
Cannot make that estimate right now. I hope that somebody has some code or some formula that can estimate that. We were not able to do that. I'm sorry, we didn't have the capability to do that, but maybe there are some codes that can do that with our input. It will be great to do. Yeah. I cannot say how much, because it really depends. Since we don't have the lab measurements to even estimate the true ejecta production rate, for example. We know how much energy is delivered. That it's constrained quite well, but as I showed before, we don't agree with LDEX or the magnitude disagreement. So we didn't want to do some of these estimates just based on what we know at the moment.
Okay.
I'm sorry. we hope that this model will be used by, anybody can use this or can contact us and ask us, can you calculate this for us? And we are more than willing to do that. So it's super exciting to see if people can use this model for anything. The Shackleton would be great test case, for example.
Okay.
Right. So the third and the last paper is original volatiles at Ceres, and then we include also the Moon and the Mercury. So the idea was just to expand the Ceres, because Ceres was interesting from many reasons, but Kuiper's 2014 detected some water exosphere, and there was no explanation that would exactly explain why did that happen. And there was no connection to meteorites, so we saw like maybe we can explain it with meteorites. And there were also a lot of areas from COM 2019 with water absorption features. So we decided, okay, let's take the meteoroid model and let's update our ray tracing code that was not efficient enough to do series for its entire period, and just do the entire series. So our goal is to, again, produce high resolution maps and see how the entire surface of Ceres is processed, or what meteorites create on the surface of Ceres. And again, the tools we used and the maps are available online. So the orbit of Ceres is different from Moon and Earth, and so it's takes much longer, 1682 days. It's in the main belt. Its orbit is slightly eccentric and slightly inclined in degrees. So you can expect something different. This is just the orbital diagram and shows you how Ceres is moving in the solar system. So if you look at a meteoroid ornament Ceres, it's much more complex than what we see on the Moon. So Ceres itself is submerged in these two source populations, the Jupiter family comets and main belt asteroids. So we would expect that the dust cloud that they generate is much more sensitive to the orbital position of Ceres. And that's exactly what we see here. So here we see on this plot heliocentric distance versus the meteorite mass flux. And the mass flux is dominated still by Jupiter family comets, as it was on the Moon. And then the three other sources are sort of equal, at least in our model. And you see that the color coding is distance from the ecliptic. So you get always the highest local maximum when you're crossing the ecliptic. And also you get some scaling with the heliocentric distance. The closer you are to the sun, the more dense the cloud gets, so you get higher mass flux. Very interesting thing was that for Jupiter family comets and main belt asteroids, the motion of Ceres was much more significant in terms of mass flux than what we see for long period comets, which is exactly what we expected, because long period comets come from way beyond Jupiter or Neptune, and the dust cloud they generate is less susceptible to orbital changes of some object in the inner solar system. So when we can calculate immediately the mass flux at Ceres, this is a globalized map over one orbit. And this might look like a very dramatic map, but it's actually not. It's the the variations themselves are in terms of percent. Again, the mass flux is 4.52 times 10 to minus 17 kilograms per square meter per second, plus minus really 1 to 2%. The highest mass flux is actually on poles, or in these close to the poles, around 45 degrees from the equator of Ceres. And yeah, we again see that there are no permanent shadow regions. So no surprise there after what we saw for the moon. When we calculate the mass production rate, projectile mass production rate, then we get, again, concentration close to the Cerean equator. There's quite a significant decrease for the poles, a factor of 2. It's quite surprising. It doesn't go to 0 for any point, any surface patch on Ceres. So still no permanent shadowed regions. These 9 different regions are regions from COM 2019 that had water absorption features. So we can see that here that all of them are affected quite similarly by meteorite impacts. And then one thing that we calculated here was also the surface e-folding lifetime. It's how we calculated it. We just calculated the area of meteorite-induced craters per unit of time, and then we just did 1 over that quantity. So that gives you what is the e-folding lifetime of one surface patch to be covered by craters. So it doesn't give you, since it's stochastic process, it doesn't give you 100% coverage in some time, but it gives you 1 over E coverage in these lifetimes. And you can see it's 1.25 million years almost around for the entire surface. So it's again, it doesn't vary that much with the latitude on Ceres. We assume that each meteorite creates a crater at 60 times large in area based on some laboratory experiments. So here I show the 9 areas that we had from COM et al. And the quantities that we checked for them. So the mass flux, energy flux, jet production rate, and the timescale, the unfolding timescale. And you can see that even though the features are located on different positions on Ceres, they experience quite similar effects. So as I said before, this area is very interesting because they were having water absorption features. And so we wanted to know, can we deliver some energy or some ejecta into that? And the answer is yes. From the point of view of meteorite bombardment, they should not differ by more than a few percent. So the local topography itself had some effect, mostly for the ejecta production rate. We saw 75% difference between the highest and the lowest value for some craters. So it was quite important, but it couldn't go to 0. So there were no permanent shadowed regions. Then you could look at the temporal variation. So this was sort of a model for the one orbit averaged over the entire orbit. But then we can do the orbit, we can see how it changes within the orbit. And so that's what we show here. So on the left side, you have the 9 areas from COM et al. 2019. On the right side, you have the global area. So we did the latitudinal strips on Ceres. And you can see that you started at perihelion somewhere here. The north and south pole, northern hemisphere, southern hemisphere are sort of equal. And then once you go away from perihelion, the northern hemisphere experiences the maximum of its mass flux. Ejecta production rate also increases, and the surface e-folding lifetime decreases proportionally. Then in the aphelion, both of them meet, and then for the southern parts, they experience the maximum of their mass flux and the ejecta production rate. So within one orbit, you can see that for half of the orbit, the northern hemisphere is more exposed, and for the other half of the orbit, the southern hemisphere is more exposed. So it's very interesting to see that. And when we did the latitudinal cuts, we could effectively see like, okay, we can have some global effect, and we can predict for any surface patch quite efficiently what that yearly variation will look like. So that was kind of interesting because we could get almost some analytical prescription how the meteor environment will behave on anywhere on a series. So once we got this, we decided, okay, how do we compare to Mercury and the Moon? And this is what we got. So this is an excerpt from a table, and it shows effectively the ratios that we get between Mercury, Moon, and Ceres for different quantities. And what we get is that the mass flux on Ceres is 50 times smaller than on Mercury, and the Moon experiences 5 times less mass flux than Mercury. The energy, the elevate energy or ejecta production rate is around 400 to 700 times smaller on Ceres than that on Mercury. The surface e-folding lifetime 74 times smaller on Ceres than Mercury. So Mercury is processed much more efficiently by meteoroids than Ceres and the Moon. And that's quite interesting, because for Ceres we found out that the meteors themselves do not deliver enough energy effectively to produce anything meaningful, while on Mercury the effects might be very strong, up to 700 times or 400 times stronger in terms of energy or the ejecta production rate. So our next project will be actually this year looking at Mercury and some permanently shadowed regions there. So from this study on Ceres, we got that, again, no permanently shadowed regions are permanently shadowed for meteor bombardment. The local topography can be important, but only for ejecta production rates. Something 75% difference was recorded for various surface patches. So what we get is that we get the equatorial regions of Ceres produce approximately 80 times more ejecta than the polar regions, which maybe is important, maybe not. But again, as I said before, compared to Moon or Mercury, the median value of the production rates are much smaller. All these areas that were shown in at 2019 should experience similar effects of meteor bombardment, so we don't expect anything important from that. When we compared the production rate that the meteorites could produce and the water exosphere production rate that was required to sustain the observation that Kuipers made in 2014, we were orders of magnitude lower with meteorites than what Kuipers needed. So meteorites are not a solution to that problem. The seasonal variations are quite huge, a factor of 3 to 7. So it might, if you have some meteor-related phenomena, it might depend when you look at Ceres. It can be quite different. If you look at the northern hemisphere in a long time, you can get a factor of 5 difference. And as I showed before in the table, Ceres experiences 10 to 50 times smaller mass flux, depending where you are, Moon or Mercury. And for energy and ejecta mass production rate, it could be much higher difference. So with respect to Mercury, you can get 600 times less energy or ejecta production rate. So the surface itself should get processed much more on Mercury than it will get on Ceres. Factor of 74, that's what we recorded as the average factor. So also Moon is getting saturated by craters from meteorites 12 times faster than Ceres. So we find it quite interesting. So the general conclusions from this is that we have dynamical models which are readily available for anybody. Just let us know. We can calculate almost anything you need. And there are no permanently shadowed regions if you take it from the point of view of meteorites. Meteorites can get anywhere on any airless body in the solar system, at least in the inner solar system. the closer you get to the sun, the higher energy is delivered by meteorites. So you have bigger effects of meteor bombardment. And the closer you are to the ecliptic, the more flux you usually get. So if you have some asteroid or a comet that is flying very high above the ecliptic, you might expect very low mass flux or very small effects when it's way beyond the ecliptic. But once it gets to the ecliptic, you can expect much stronger effects. And what we see in general, that the more inclined slopes are excavated much faster than the crater floors when you are on lunar poles or when you are on poles of anybody effectively. We expect the same thing for Mercury as well. And I think that's it. Thank you.
All right, awesome. Thanks, Peter. That was super interesting, and yeah, really nice work. So we are almost at the hour, but I think since we were asking questions in between, but I think we have time for maybe one more question, if anyone has one.
Hello.
Hi, Yuchi, go ahead.
Oh yeah, I have a question. It's not closely related to volatiles, but related to the credit countings, because I saw your models for the impact flux or meteorite flux for the moon and for other planets. So I want to know how long can your model, impact flux model, go back to the past, because it obviously has very strong interpretations for the credit counting work for the moon or Mercury, because when you see like maybe for a surface in the polar regions and surface in the equatorial region, and it has different crater densities, but maybe just the polar regions, the crater density is low just because the flux is low originally. So I want to know how long can your model go back to the past, and the size of your craters your model can evaluate, like craters smaller than 1 kilometer, craters smaller than 100 meters. This is my question.
Okay, so these are small meteorites. So the largest meteorite in the model is like 2 millimeters. So they create very small craters that are, micro craters. So I don't think you can see them from a spacecraft or anywhere. So it's really small stuff. In terms of how far you can go back in past, it's difficult to extrapolate it way beyond, I would say, 10 million years or 100 million years, because we don't know how the zodiacal cloud looked like in the past. We have models for the source population, so we know how the main belt and the other source population like Jupiter family comets, Early type comets evolve, at least from what we see today. So we can expect the rates, how they populate the solar system and how much dust they can create. But beyond 100 million years, I would not go with the zodiac cloud model or the meteor model.
Thank you.
But these effects are more like, short term, because when you have meteorite bombardment is really happening constantly. So, and since we have only small particles, they cannot penetrate deep the surface, the deeper than few millimeters, let's say. So I was not afraid that the model will not be valid for like hundreds of millions of years, because the effects should even out, I think. But it's possible that the zodiacal cloud was much denser in the past. Yes.
Yeah, thank you.
All right, so so in the interest of time, I think we have to wrap it up for today. But Peter, thank you again. And can people reach out to you via email?
Of course, yeah.
If they have questions? All right.
No problem.
Okay, so in that case, thanks again, and thanks everyone for dialing in. We will meet again about a month from now.
Thank you.
All right, bye everyone.
Bye.